observed that people are still. So in one missing step, it's a small step, but I still want to point out what I missed. So I applied lemma 4 to these two functions, f and g, right? So we applied lemma 4 with f of t equal to 1/2 t log t and 1/2 log 2 pi plus minus t over 2 pi minus t log n. And we apply that with g of t, the t over 2 pi to the 3/8. So in doing so, I calculated f prime of t and f double prime of t. And you notice that f double prime of t was at least 1 over t. And I said, okay, lemma 4 gives them. But there was one other condition in lemma 4, and that is a condition on f prime over g prime and the number of zeros that this has. So if you do this calculation, you find equal to 0. So how many times? That number was called q in the lemma. And if you use this f and g to calculate that, you end up with showing the equation becomes something like, if you call this c, I'm going to call this c, it comes to be c plus half over t minus log n times 3/8 or something. And this clearly has, for each n, at most, one solution. So q is either 0 or 1. So you have to use the quotient rule and then do a little calculation. You end up with this. So this is important because in the upper bound, remember, you not only have the m, which is this, you got to multiply by q plus 1. So if this thing becomes out of control, then this proof will break down. So we just need to, I had missed one step. So there is only one solution at most for that equation. So otherwise everything goes through. Okay, sorry about that. Now let us go to something about the size of the Riemann zeta function inside the critical strip. Okay, so some comments and some observations. And I will prove a theorem of Turan connecting partial sums of the Riemann zeta function with the Riemann hypothesis. Okay, so first, size of zeta s inside the okay. So we'll define for 0 less than or equal to sigma less than or equal to 1, define mu of sigma to be the inf of all nu, such that zeta s is equal to capital O of t to the nu when real part of s, that is sigma, is equal, when real part of s is fixed and is equal to sigma. So you look at the critical strip, take any sigma, and on that line, calculate that t to the nu and look at the inf of all those. That's called mu of sigma. So what do we know about mu of sigma for now? We know that mu of 0 is 0 because zeta of it, I mean, this is apart from here, we have to go beyond here, okay, is capital O of log t, so t to the epsilon for each epsilon greater than 0, provided, let's simply say, absolute t is at least 1. You have to stay outside of 1. I mean, that's 1 over s minus 1. It's a pole. Apart from that. So mu of 0 is 0. We just proved, in the course of proving Hardy's theorem, that mu of 1 is 1. So if you want to draw the picture of the mu function, it's 0 here, and it is 1 there. This is the mu function. Okay. So by Fragment-Lindelof, mu sigma is no more than this. So mu sigma is lower than this. So by Fragment-Lindelof, we get mu of sigma, and we use this. It's less than or equal to. So what are the equation of the straight line which connects these two, right? It's 1 minus sigma over 2, correct? Is that a correct statement? Or is it?
It might just be 1 minus sigma.
This is half, isn't it? I proved that mu of 1 is half, I think.
Yeah.
In 1, so that's right. 1 half. The picture is wrong. Okay.
Yeah.
So it's 1 minus sigma over 2. Which means mu of half is no more than 1/4. But we do not know what exactly mu of half is. All right, so this height is, mu is, it's like this, by Fragment-Lindelof. Now, let me mention something in this connection. Why is this of some importance? So let me state the Riemann hypothesis. So this is one of the millennium problems. So this says that zeta s equal to 0, 0 less than sigma less than 1 implies sigma equal to half. So this is the Riemann hypothesis. There is a hypothesis due to Lindelof himself. Okay, that's also unsolved. It's called the Lindelof hypothesis. That hypothesis says that mu of 1/2 is equal to 0. That is, zeta of half plus it is capital O of t to the epsilon for every epsilon greater than 0. So this is the Lindelof hypothesis. And there is a known theorem, we'll call it LH. There's a known theorem that, so this is a theorem. The Riemann hypothesis implies the Lindelof hypothesis. Okay. All right, now why is it that one is interested in statements about the size of the Riemann zeta function, either on a vertical line or in particular on the half line? So there is a famous theorem of Ingham. I'm going to say Ingham's theorem for you. 1937. That's when he became very famous. And Ingham's theorem says that if mu of half, we'll just call it C. We don't know whether mu of half is what we know exactly. We're conjecturing mu of half is 0. But let us say mu of half is less than or equal to C. Then the gap between consecutive primes is capital O of n to the power lambda epsilon, where lambda is equal to 1 plus 4c over 1 plus 2c. This is Ingham's theorem. So let us understand this theorem in the context of what we have done. So actually Ingham proved something stronger. It's not just that the gap between consecutive primes is like this. Ingham actually showed that the number of primes in the interval x plus x to the theta minus that is the interval x to the theta is asymptotic to x to the theta over log x for theta greater or equal to lambda, greater than lambda. So not only does there exist a prime number in this interval, there exists, you can find an expected number of prime numbers in this interval. So it's a prime number theorem for short intervals. Now, this kind of a theorem you can deduce if you had a strong form of the error term. So you then apply this at that point, subtract, and so if the error term of the prime number theorem is as good as this, then this follows. But to get the error term of the prime number theorem as good as this, you would have to move the line of integration to that point. But Ingham's point was it's not necessary to move the line of integration to that level. What is important is to get an understanding of the size of the Riemann zeta function of the half-life. So it's another approach. Okay. So there are possible topics for us for the next semester, either to go in this direction, more and more of the theory of the Riemann zeta function and prime numbers, or vary the topic a little bit, like doing, for example, sieve methods. Primes of the form p plus 2. Not that we'll prove that. We'll prove that infinitely many primes for which p plus 2 has at most, a certain number of prime factors, like 6 prime factors or 7 prime factors, not very difficult. But if any improvement of these things becomes more and more difficult. Okay. All right. So I'm just giving you a flavor of in what directions the subject could be developed, given the body of results that we have proved. Okay. So this is Ingham. So this actually is proved. We can call it a prime number theorem for short intervals. That's what this is. Okay. So this is a PNT for short intervals. All right. Now, we already know mu of half is less than or equal to 1/4. I mean, already with our present state of knowledge, right? So we know C is less than or equal to 1/4. So I can put actually C equal to 1/4 here. The smaller the value of C, the smaller the value of lambda. So I can put C equal to 1/4. So C equal to 1/4 in, we'll call it 1, yields Pn plus 1 minus Pn is capital O of n to the 2/3 plus epsilon. So if we prove Ingham's theorem, then with our current estimate on mu half, we will get 2/3 plus epsilon. No, it's quite 2/3, right? It's 2, wait a second. Yeah, 2 plus 4c. 1 plus 4c over 2 plus 4c. My apologies. Put 1/2 of it. Okay. Yeah. The earlier one was making it bigger than 1, which is useless. 2 plus 4c. There was 1/2 or something else here, and I copied it incorrectly. Okay. So this gives you 2/3 plus epsilon. But by the time Ingham proved his theorem in 1937, Hardy and Littlewood had already improved this mu half to 1/6. So already in 1937. Hardy Littlewood had proved mu of sigma, or mu of 1/2 to mu 1/2 less than or equal to 1/6. And this stood as the best result for quite some time. So with C equal to 1/6, one gets Pn plus 1 minus Pn is capital O n to the 5/8 plus epsilon. So, when I arrived in Ann Arbor in 1974, right? When I arrived in Ann Arbor in 1978, or maybe when I first met Montgomery in 1973, he had already become famous for having proved in the early 70s Pn plus 1 minus Pn is capital O of n to the 3/5 plus epsilon, but without using this theorem of Ingham by a new method. So he basically broke an impasse of more than 30 years, but by a new method. Now the Riemann hypothesis in this context, so we can simply say 3 improved by Montgomery. And there have been further improvements, but 1970s to Pn plus 1 minus Pn equal to capital of n to the 3/5 plus epsilon. But not using Ingham's theorem, not by an Ingham's theorem. Now let us look at the Riemann hypothesis. Implies Pn plus 1 minus Pn is capital of n to the half plus epsilon. In fact, we don't even have to say Riemann hypothesis. We can say little log hypothesis. Little log hypothesis is this is not 0. So if I put 0, I get 1/2, but 1/2 plus epsilon. So the gap between consecutive prime is capital of n to the 1/2 plus epsilon as per the little log hypothesis, which means that's what the Riemann hypothesis means. Now, this is not necessarily the best thing, right? I mean, we expect the gap between consecutive primes to be actually capital of Pn to the epsilon, n to the epsilon, but this is what the Riemann hypothesis is. All right, so this is just to give you a background on some of the things that are possible. Okay? So now, let us move on to some theorems relating to oscillation theorems. Okay, but I will now mention an equivalence theorem for Dirichlet series, which comes from the Bohr theory of Dirichlet series, and it's going to be related to what you're going to be talking about in the last week. And after I give you the notes, you can tell me whether you want 1 lecture or 2 lectures. Okay. All right, so let's look at some oscillation theorems for Dirichlet series. But before that, let me define equivalence of Dirichlet series as per Bohr. So two Dirichlet series, so the definition. Two Dirichlet series summation A n of AS and B of S equals summation B of n into S are equivalent. This is the definition. Well, actually, the definition of equivalence given in Apostle, following Bohr's theory, is a little bit different, but then he has an if and only if. So I'm going to use this as the definition for my purpose. Okay? Are equivalent if I can write Bn as An times f of n, where f of n is completely multiplicative. So this is 4. Where f of n is completely multiplicative. And one more thing, the absolute value of f of n is 1 whenever an is non-zero. So we don't actually care when an is 0 and bn is 0 what the f is, but when they are non-zero, they are connected by a multiplicative function whose absolute value is 1. Okay, so this is the definition of equivalence. And one can show that this is an equivalence relation. All right, but now comes a very nice theorem of Bohr. And we'll use this theorem, Bohr's equivalence theorem. So even if you don't prove this theorem, hopefully you can give an idea of what goes into the proof of such a theorem. And that discussion will not just be for Dirichlet series. You will see that from the notes I give you, that discussion will be for generalized Dirichlet series, which are equal to an e to the minus lambda n s. And this is the case where lambda n is log n. Okay, so Bohr's equivalence theorem. It's a very nice theorem. The Bohr equivalence theorem says, let A of s equivalent to B of s, right? Dirichlet series have sigma A as abscissa of absolute convergence. Now here is the theorem. Then, it's a very, very nice theorem. Then, in every half plane, sigma greater than sigma 1, greater than or equal to sigma A, go to the right of this, at any point, for two Dirichlet series, take an identical set of values. It's fantastic. So what is it we are saying here? So this is sigma A. You choose any sigma 1 to the right of sigma A and look at this half plane. The collection of values that each Dirichlet series takes in this half plane will be an identical set of complex numbers. But of course, different values are taken at different points by each A and B, but the total collection of values taken in this half plane by A will be the same as the total collection of complex number of values taken by B. And you move this to the left, you get a larger collection of values. That larger collection of values will be identical to both A and B. No, so you can go all the way, so technically you can go all the way up here, but it doesn't say anything about the boundary. Because it could be that one of the series is absolutely divergent on the boundary and the other one is absolutely convergent. I mean, one could be convergent and the other could be divergent. So we have to be a little bit careful. We don't know what the values on the boundary are. Okay, so this is the definition of the two Dirichlet series. Being equivalent and major concept of Bohr's equivalence. Okay, so now what we are going to do is this. We're going to consider two functions. Okay. Consider, so application. So consider zeta ns. This is the truncation of the Riemann zeta function. And so on. And x. Okay, and summation lambda n over n to the s and less than equal to x. What is lambda? Where lambda, the Liouville's lambda function, minus 1 to the total number of prime factors of any Liouville's function that you discussed in your homework. Now clearly the two series are equivalent as truncated series for every x. Okay. Clearly, for each x, zeta n, zeta xs is equivalent to this truncation of the Dirichlet series. Because I don't care, after the x position, this is 0 and this is 0, so I don't care what the multiplicative function connected with this. But to go from this to this, I have to multiply by lambda n, and the absolute value of lambda n is 1. So these are equivalent Dirichlet series. So they will take the same set of values. So here is a theorem first proposed by Turan. And we'll show in another 10 minutes that this theorem is false. But here is the, and then we'll modify the theorem, and that theorem still holds. Okay, so Turan's theorem. So Paul Turan is a great friend and colleague of Paul Erdős. Erdős was the champion of analytic number theory, of elementary number theory, and Turan was the champion of analytic number theory. And Turan was a good friend of Selberg. So it was to Turan that Selberg gave a copy of his notes on the so-called famous Selberg identity involving the lambda function, which is a major step toward the proof of the prime number theorem. So Selberg's controversy was with Erdős, but he had no qualms about Turan. But Turan gave the talk, and Erdős attended the talk, and that is how the controversy erupted. Okay, so, all right. So here is the theorem, Turan's theorem. If there exists a knot such that, we'll now use an integer, zeta ns is not equal to 0 for all n greater than or equal to n naught and sigma greater than 1, then the Riemann hypothesis. Quite amazing. The Riemann hypothesis is a statement about the Riemann zeta function first defined as an infinite series and later continued analytically. And Turan's theorem is about the truncation of the Riemann zeta function at this point. And now that truncation can be defined everywhere in the complex plane, right? Because it's just a finite series. Therefore, a statement on the non-existence of the zeros of this truncated function at sigma greater than 1 implies the Riemann hypothesis. So let's prove this and then see where we possibly, how this later the trouble comes. Okay, so let's prove this theorem. Okay, so first thing is,
may I ask a quick question? So
Yes.
this is the motivation here is sort of that the zeros of the zeta function start clustering as you go up the real part 1/2 line, right? Like they
correct.
become, yeah, they become
more
more
and more
numerous.
dense because of the t log t.
And so he was hoping that they reach some accumulation point at some.
Actually, this is going to come out of Landau's theorem.
Okay.
Let's see the proof.
Okay.
The proof is going to be quite, it's a beautiful application of Landau's theorem. So first thing is, okay, but before we even do the proof, let us first look at the series, okay? So we know that summation lambda n over n to the s is equal to zeta 2s over zeta s. We know that. It's sigma greater than 1. That's one of the early results. But now, I'm going to do something else. Put C of x equal to summation lambda n over n less than or equal to x. Let's do this first. All right. Then, summation lambda n over n to the s, n less than or equal to x, can be written as the integral 1 minus to x, 1 minus to x, 1 over u to the power s minus 1 dc of u. Do you agree? So I get the extra lambda n over n from this. All right? Which is equal to integrate by parts. This is in sigma greater than 1.
So the left-hand side here doesn't have an S though.
So maybe I should have said that. Correct. S is okay. Yeah. Is this. So you agree, because this is, the jump is lambda n over n, and that has the extra. Okay. This is sigma greater than 1. So this is equal to C of x over x to the s minus 1. Now sigma is greater than 1, by the way, because the lower limit becomes 0 at 1 minus the integral from 1 to x, C of x, that's C of u, du, over u to the power 1 minus s, right? So that is minus 1 minus s, so I can put a plus s minus 1. U to the minus s. Okay, so now if you let n tend to infinity, x tend to infinity in 5, this becomes 0. So we get summation lambda n over n to the s, which we already know is zeta 2s over zeta s, is s minus 1 summation c of u du over u to the s, which implies that zeta 2s over s minus 1 zeta s is the integral from 1 to infinity c of u du over u to the s. And this is in sigma greater than 1 for now. By the way, why did I make this go to 0? Why did I say this is 0? Because the denominator is sigma greater than 1, so this is bigger than some small positive power of x. C of x is this truncation. And you can do a simple upper bound for the truncation. Lambda is no more than 1, so there's no more than log x. So there's a little bit going on here. So this is no more than log x over x to something that goes to 0. That's what I used as the absolute infinity. Now let us understand 6 in this context. So now we're going to say that, so we'll call this the Turan hypothesis. TH not theorem, Turan hypothesis. Okay, Turan's hypothesis. So